Okay, welcome back, Iris. How are you doing?
Yes, I'm fine, thank you.
Sure. Do you have any questions about previous material?
Not really.
Did you start working on the homework?
Yes.
Sure. And then where are you now? Which did you? How many problems did you solve? Is it? Are you doing it on time?
I'm doing the last problem in section 1.2.
I see. Okay. So today we should finish the whole chapter 1. So we'll go a little bit faster. So I think we did more like a lot of calculations with reducing matrices to echelon form. So today we'll talk more about we'll talk about spans. We'll talk about vector spaces. We'll talk about linear transformations and stuff like that. So the plan for today will be to cover 1.4 through 1. Till the end, but like we're not going to do everything, so I'll look at the theorems and look at some examples.
Okay.
Yeah, sort of. In fact, we did some material we already did from later sections, so this is okay. Good. So last time we talked about linear combinations of vectors, right? So remember, if we have a set of vectors v1 through vp in n-dimensional Euclidean space in Rn, then we have a we can have the linear combination is the following formula. It's the sum of, you can also write it like this, right? There's a summation symbol ci vi, I goes from 1 to p. And so you've probably seen it, right? It's a sum. So that's what this formula means.
Yeah.
Right. Now we call the combination trivial if all c's are 0, and it's non-trivial if at least one of those ci's is non-zero. Now and then we had these examples last time with integer coefficients, which gave us some lattice of numbers. So now let's give a definition. So again, let's take these vectors v1 through vp in Rn. So these are vectors. And now let's consider the set of all possible linear combinations of these vectors. Of these vectors. Right, and then we'll call it span. Span of v1 through vp. So that's set of all c1 well, let's just say it's the so it's the following thing. It's set of c1 v1 plus and so on plus cp vp such that we can take each ci is inside R. Right. Let's assume that they take values in reals. Right. So it's all possible linear combinations, including trivial one, right? So for example, we can take 0, 0, 0, 0 everywhere. Oh, hi, Sophie, you just joined. So we're talking about spans of vector spaces. Spans of sets of vectors. So just repeat, so span of vectors from v1 to vp is the set of all possible linear combinations of those vectors. Okay. Now, that's what it is. So let's look at some examples. Let's say P is equal to 1. And N is equal to, for example, 3. So we have a vector V with V1, or we can just call it V inside R3. And let's take a particular vector. Let's take vector V1 with components 1, 0, 0. So if you draw it in 3 dimensions, we have a coordinate system like that, right? And this vector, so that's our vector V1. So can you describe the span of V1? What is span of V1? Given the definition. Well, the situation is a little bit degenerate because there's only one vector. So the only thing you can do is to multiply this vector by a scalar. So if you multiply this vector by all possible scalars, what are we going to get?
So 1v1?
Just single vector, yes.
How to write?
I mean, you can just tell me. I mean, you don't have to. So what is it? So it's a set of all C1s such that when you look at that, so C1 multiplied by V1 for all possible C1s.
Oh, okay.
That's what span is, right? So if you take a vector and you multiply it by every possible number, what will it give? You can describe the answer in one word, right? Okay, maybe 2 words. So if this is V1, let's multiply V1, for example, by 2. So that's 2V1, right? Then let's multiply it by -1. That's -1 times V1. And you can multiply it NV1. Right, so n here can be any numbers. It doesn't have to be integer. You can multiply it, for example, 1.6, like or square root 2 times V1. So if you do that, it will be somewhere here, square root 2 times V1. And now imagine that you multiply it by every possible number, every possible real number, positive or negative or 0. So what will be the set of points which you will get by, so remember, a vector, there is a one-to-one correspondence between vectors and points in Euclidean space, right? Because the tip of the vector represents a point. So what this is as a set of points in R3? So here I give 4 examples, right? So endpoints of each vector is a point where, like, how would you describe the set which contains all these endpoints, all tips of all these possible, of all these vectors, including 0. What is it? Actually, I think I drew it incorrectly, right? So what I drew was for the vector 1, 0, 1, 1, 0. So it goes along the y-axis. Yeah, I apologize. So it will be the line, right? It will be the entire line, the whole y-axis. Everything. So indeed, so where so C1 times V, C can be any numbers, and V is a vector of fixed length. Now, when you multiply a vector by a constant, right, you get a vector in the same direction if a constant is positive, and its length is scaled by that constant, right? So here we have some examples. For example, vector 2v1 will have components 0 to 0, right? And then if you multiply it by any number, so vector C 1 times v1 will have components 0, C1, 0. And C1 can be any number, so you would you will recover all points on this line on the y-axis. So therefore the span of single vector is a line, right? We can also say that this is the same as R, as a set, right? Do you agree? Is that clear? So a span of a set of vectors is a space. It's a set of points. It's an infinite set of points. Right. Okay, so maybe if this is not completely clear after we solve the next exercise, it will be easier what's going on. So let's say we stay in 3 dimensions. Now let's keep p is equal to 2. Yeah, and then n equals to 3. And now let's say we take 2 vectors v1, which has coordinates 1, 0, 1, and v2, which has coordinates 0, 1, 0. What is span of v1, v2? Describe this set. Meanwhile, I'm going to draw while we're thinking.
So is the n means how many?
So n, right? So it's in the definition. So the definition it's written here. So you see it says we fix 2 integers, p and n. N is the number of components in each vector, right? It's the dimension of the space. And p is the number of vectors. So in the first example, we had 1 vector in 3-dimensional space, and that gave us a line, right? The fact that it's a 3-dimensional space didn't really matter too much, right? So if we had a 10-dimensional space, it would still be the same. It will still be a line, right? Just all other components will be zeros. Okay. Now let's now go with the 2-dimensional example. So vector v1 now is here, and vector v2 is there. So describe the set of all possible linear combinations of these 2 vectors, such that C1 and C2 are in R. What is the set of points? So I have selected n equals 3, so you can draw it on a template. Otherwise you can only write formulae. Sophie, you're muted. If you say something, I didn't hear.
So it's gonna be a
I didn't hear the last word. It's going to be what?
C1, C2, 0.
No, they don't have to be. They have to be. They're not equal. They don't have to be 0. So we are. What we're doing, we're taking the linear combination. So we're calculating the sum for all possible values of C1 and C2. For example, 1 and 1, 1 and 2, 10 and 15. And we look at all possible values. Okay, so let's maybe look at some, for example, let's look at some examples and we'll see immediately what's going on here. So yeah, I'm glad that we're discussing it in greater detail. So say, let's take C1 is equal to, for example, what is V1 plus 2V2, right? So it's a vector that looks like this. So that's 2V2. And if you add them together using parallelogram rule, right, you'll get this vector, so this point over here. Let me not.
Diagonals of the plane.
Yeah, that's right. So so here, so this point belongs to the plane xy because these two vectors belong to xy. And now, if you look at all possible combinations, all possible values of C1 and C2, you will have counted all the vectors that look like this, right? So that live in this plane, right? So every point in this xy plane can be. In fact, it's a statement that you already know, right? So every point in the xy plane and the Cartesian plane can be given by a pair of two numbers, right? And here this pair of numbers is C1 and C2, right? So that is equal to the span of two vectors is the plane. It's a plane which is a subset of R3. Here is the xy plane. Do you agree? Which part of the definition of the construction do I need to explain again, if it's not clear?
The equation shows us the R is that.
I didn't quite hear it well. Can you type maybe, or? So here again, so we look at one example. So this vector in blue was V1 plus 2V2. Now let's take another combination. Let's take 5V1, or 5 is probably too long here. It would be 3V1 say minus V2, right? Where this point will be. So 3V1, we'll do it 3 times. That's 3V1, and minus V2 is there. So we'll find the parallelogram rule, and this vector will be here, right? So it's this point on the plane, and you can imagine that as you change all the parameters, you will find all other points on the plane, on the xy plane. So this is no. It's a subset. Yeah. It's a set theoretical notation is a subset. So which means that it's set of all points x, y, 0. And then here R3 is represented by set of triple of points x, y, and z. So this plane sits at the position z equals 0. Yeah, so this is the span. Okay, and now maybe let me give it different examples. So different examples now you should be able to tell me for sure. So what would be span of vectors v1? Well, let's put different letter. Vector A and B, where vector A has coordinates yeah, so it's 0, 1, 0, and vector B has coordinates 0, 0, 1. Which space is that?
Sorry, Peter, I have no idea about what that R means.
What means the span or the R?
The R?
Where's R?
It's like you write it below, above the, yeah, that's right.
This one, right. So R, right? So R is the set of real numbers. Right, so which you can write as a line. Right, so this is x line. So you have a point x. It's an element. It's a real number. Right, for example, x equals square root of 2. So it's a set of real numbers. R squared, which is the same as R times R, right? It's a set of ordered couples x and y, such that both x and y are real.
So the x, y is like means in the plane, all the number, all number displaying are real number.
Both x and y are real here. Yeah. So that's why we identify R2. So we say that R is a line. R2 is a plane, right? And then R3 is the three-dimensional space. So R3 is, is R times R times R, right? It's the set of triples, x, y, and z, ordered triples, right? The order matters, such that x, y, and z, each of them is a real number. So every point in this three-dimensional space, say here, is represented by 3 real numbers. So we denote this R3. Does it answer the question?
I got it. Thanks.
Sure. Yeah. So you might just I assume that you are familiar with notation, but yeah, if not, then I think I discussed it with Iris yesterday when you were offline, but that's fine. Good. So are we clear on the planes? Basically, denote it with R2 or not. The construction should be clear. So if you have two vectors, right, which are not parallel to each other, so there are two different vectors like this. So they lie in a plane, right? So if you take the span of these two vectors, which means that all possible linear combinations of these vectors, you'll get the entire plane in which these two vectors lie. Okay. So what would be the span of vectors A and B in this case?
It's a plane between y and z.
Yep, absolutely. Yes, that's right. So this is the this is the YZ plane, because the combinations, a set of linear combinations of these two vectors, say C1A plus C2B, will provide you, will give you a point on in the YZ plane. Yes, absolutely. So this way you'll have, if you have two vectors, then you'll get a plane. Span of these two vectors is a plane. Now, and then the last question about the spans, and we'll move on. What's span of vectors v1, v2, v3, where v1 is equal to 1, 0, 0, v2 is 0, 1, 0, and v3 is equal to 0, 0, 1.
It's gonna be like a three-dimensional shape.
Yeah, everything, the entire space, right? So that's not the way to say it. Yeah, that's right. Now, remember we talked about last time about we talked about linear dependence. No, we haven't talked yet. We'll talk about this later. Good. So that's the concept of span. I hope it's clear. It's clear by now. So, but just to make sure, there's one more subtlety. So what we had so far, the number of these vectors give you the the dimension here. However, if some of these vectors are parallel, right? So let's say you have two vectors which are parallel to each other, then and you take a span of them. So then you don't get anything new because you already have one vector, and the other vector is just a scalar multiple of the same vector. Right? So if you say you have a vector v1 that goes this way, and vector v2 is just parallel to it and has a smaller or bigger length. So then if you do span, if you do span of these two vectors, you're still going to get the line. So this is the line that contains vector v1 or v2, right? So vectors, they must be different. They should not be parallel for this to happen. We'll come back to that in a moment, a bit later. Okay. Yes, I think it's the last time I think we finished with solution of the homogeneous system of equations, right? So we have, if you have a matrix A multiplied by vector X is equal to 0 vector. Homogeneous now, if A is the matrix n by m, right? So we can rewrite this equation like this. We can write it as A1 times x1 plus A2 times x2 plus and so on plus A m times xm. So let's say x is equal to 0. So if say A is the n by m matrix, meaning that it has n Nicholas n rows and m Michael columns. Right, so it's a rectangular matrix like this, right? So it's n by m. So you can multiply it by a column vector with m components. Now these two statements are equivalent. Now I think I put vector. I shouldn't put vector on xm. Yes. So in other ways, this homogeneous system of equations, if it has a solution, it means that there is a linear combination of the column vectors of the matrix A1 through AM, which is equal to 0. And so this is the matrix. You can pick a column here. I'm not putting, so this is the AI, right? It's the ith vector. And then the linear combination should be equal to 0. So as we discussed last time, we can always find a trivial linear combination. So if you say that all x's are 0, if x1 is equal to xm is equal to 0, then the left-hand side is automatically is trivially 0, and the equation is satisfied. Right. So an interesting question would be if there is a non-trivial linear combination when this is true, and we have shown last time that it is possible only if and only if in the solution of this linear system of equations there is a free variable. In other words, a non-trivial solution exists. If yes, if there is at least one free variable. So in other words, the echelon form of the matrix should look like this, right? So this is the matrix, then its echelon form should look like that, so that there will be not all columns are pivot. In other words, so if these are pivot positions, there must be some columns like this which do not have pivots, right? An example that we had last time, I think we saved it in Mathematica. We had I'm just gonna write down the metrics. We don't need Mathematica for now. So we have this matrix 3. So matrix A was 3, 5, minus 4, minus 3, minus 2, 4. You can look it up in the recording. Put it up. So this is A, and then if you take the augmented matrix, then in the reduced echelon form, the augmented matrix looks like this. So augmented. It was this, a 1, 0, negative 4/3. So you can check it yourself. Then 1, 0, 0, 0, 0, 0, 0, 0. So remember, this is the column, this is the right-hand side, right? This 0 vector over here. And this echelon form translates into the following conditions. So it's x1 minus 4/3 x3 is equal to 0, and x2 is equal to 0. So therefore x2 is fixed, and x3 and x1 they are related. So there's a well, it's a line, right? So this equation provides you the line. It's a line in R3. Yeah. So therefore, you can say that the set of solutions of this equation. So if A is this matrix, then set of solutions AX equals 0 for this matrix A above is a line, well, X 1 equals 4/3 x3, yeah, and x2 is equal to 0. So there is a one free parameter. So x3 can be anything. So therefore, so it's a line which you can think of as span of a vector. So if there's a vector v that goes along this line, then the space is the span of that vector v. Okay. In case you have more free variables once you solve a solution like that, then the space of solutions will be a span of that many vectors, right? So if you have, say, 3 free variables, it will be a 3-dimensional space. It will be span of these 3 vectors. If you have n, so if you have, say, k of the vectors, it will be k-dimensional space. And by construction, of course, they're not parallel to each other because these are different vectors. Okay. Good. Now let's talk about a non-homogeneous system. And so, any questions about this?
Sorry, what's the span of the vector here? I cannot understand.
So, you can ask, what is the vector, right? So, well, let's draw this line. x1 equals 4/3 x3. So it's the in 3-dimensional space you have. So it's in 1-3 plane, which will look like. Okay. Like this, right? So it's 2x3. So the last condition says that x2 is equal to 0. So set of points live in the x1, x3 plane, and then the first condition says that x3 is proportional to x1. So there's this vector, there's a vector v here, right, that goes along this line. And if you want, vector v has coordinates, what is it? 1, comma, so yes, it's 0 like this. Right? It's for thirds, 0 and 1. Do you agree?
Yes, I agree. Thank you.
Sure. Right. Yeah, so we can describe the space of solutions very precisely in this case. And then, okay. Good. So that's the solution of the homogeneous equations. Homogeneous means that the right-hand side is trivial. So x is equal to 0. So now let's modify this and add the add a non-trivial right-hand side. Right. So now we do non-homogeneous. So for the sake of the argument, let's keep the same. Let's keep the same matrix, right? I'm just going to copy it from the previous example. So A is equal to no vector. It's a 3, 5 minus 4, minus 3 minus 2, 4, 6, 1 minus 8, and vector B is 7 minus 1 minus 4. Okay, so now, well, we can do the same calculation of the reduced, well, you know, if you want as an exercise, we can quickly do it on a computer. So let's do it in, maybe we still have it in mathematical. Do we have it? Okay, let's do it really quick. So by now you should be pretty handy with those things, right? So the augmented matrix will look like, yes, it's 3, 5. Minus 4, 7, minus 3, minus 2, 4, minus 1, 6, 1, minus 8, minus 4. Yeah, and then let's do the echelon form. So we can add second line with the first one, right? So that will give us 0, 3, and 0, 6. And then multiply by -2 and add it with the third row. So it will be 0, -9, and do it times -2, so it's 0, and -18. So we can simplify this a little bit. Okay, so let's divide it by 1, by 3. Let's divide by -9. So you can see that these two arrows are the same, and this we can divide by we'll divide it right, so here. So then we can have we can wipe out this row. And just subtract here, and then need to do the pivot here. So multiply by -5, we get 0 and -3, right? And finally, we divide by 3 the first row. Didn't really have to do it, but just for consistency. -1. Okay. All right, so that's the reduced echelon form. Yeah. So now, well, again, there's a free variable, but the space of solutions will look slightly different, right? So we have what we have x. Now x1 minus 1/3 x3 is equal to -1. And then x2 is equal to 2. And x3 is 3, right? So these are the only these are the only conditions that we have, right? So therefore, the general solution, so the solution would look like this. So let's see, this x vector is equal to it's x1, x2, x3. So x3 is free. Just substitute the set of solutions, right? And then we get, instead of x1, we can write that x1 is equal to 1 minus 1 plus 4/3 x3. Right, so we can replace this with x3. So x2 is equal to 2, and here we have x3. Right. now let's do it. We can simplify it. Well, we can write it in the following way. We can write it as sum of two pieces. So first we take, let's write it as this, -1 to 0 plus 4/3 1, and here's x3, like that. And do you copy so far? And so basically I split the solution, the vector, into two parts, the one that contains x3, the free variable, and the one which does not contain it. So that allows us to write it x as, let's call there some vector p plus x3 times vector v, where p is this, and v is this. Okay. So, in other words, now let's try to plot it. What does it mean, right? So let's see if we can do it here. Oh yeah, we can do it here. You can do the annotation. So let's say, so vector p is fixed. Actually, if you want to, you can annotate on my slide as well, but I need to enable annotation. Actually, now it's enabled. So if you want to ask a question and write something, you're welcome to do so. So we have a vector p here, and then vector v. So see, these two vectors, they are not parallel to each other, right? So they clearly look different. And then say vector v goes like that. Right, so we can multiply v by any constant. So for example, any number, say x3. So we can continue this. So this will be x3 times v. And then when you add them together, so here we have it, we added them. So the addition would look like, well, using the parallelogram rule, like this. So this red vector is p plus x 3v. Now it looks a bit different from the span, span spam is what you get in your email. And then you can also go in opposite directions. So so that's like minus, we can go to the negative direction. So like, well, basically there will be a line. So this line is span v. And then from every point you can get this shift by p. Right. We'll go like that. So in other words, this span of v is translated by vector p, right? So remember this v. Oops, sorry. This thing, what we had before. I drew you the line, right? So the space of solutions of the homogeneous equations was span v. So this is the solutions of space of solutions of AX is equal to 0. Right, and now because we have this non-trivial right-hand side, we have this B coefficient, B vector, excuse me. Then we also add the vector P. Right, so therefore we have to move to a different position. So now this line will describe as the space of solutions AX is equal to B. Now, what does it mean in general for this? First of all, are there any questions here? So this blue line was the set of solutions of the homogeneous system, and then the black line after the translation will be the set of solutions of the inhomogeneous system. Now, how can we describe in general what's going on here? So if we have if we have an equation, so space of solutions of equation AX is equal to B, how can we access that, right? So we can, for example, how to describe any point on this line, right? Well, we know that this point is is vector P away from some point on this blue line, right? So therefore, so we can take any solution of homogeneous equation here, let's call it VH for homogeneous. And then we add here P, right? So in other words, we can start, so a solution of an inhomogeneous equation. So solution looks like this. So X is equal to P plus VH, right? So in other words, so if P is a solution, so assume that if you have found some solution of your inhomogeneous system, call it P, right? And then the claim is that the solution set of the inhomogeneous equation, right, of this one, is obtained by adding this P to any solution of the homogeneous equation. And so to get to get every point here on this line, you can get it from a point on that line by adding this vector P. Like that. That's the theorem, which we have illustrated on the example. Questions?
So P here is like a fixed matrix or fixed number that you need to add to
So
the
B,
V.
the B, so there are two letters. There's a B, the right-hand side, which is what it is. And now P here is, so say you're looking at the equation and then you just guessed a solution. You just happen to find that, by accident or by some other method. So P is a solution, some solution, okay? Now, the claim is that all solutions, set of all solutions of the inhomogeneous equation is given by this. So you take all solutions of homogeneous equation and then shift them by P.
Okay, I got it.
Yeah. So it's really like having these two lines here, the blue line and then the black line. Only that in general, the space of solutions, of course, doesn't have to be a line. It's rather some higher dimensional subspace, right? It can be two-dimensional, k-dimensional. It can be very large. Okay. Good. If you want, you can take a screenshot of this, or I can do it. It will be saved in the video. So. Okay. Great. Now, what time is it? Oh, we've been talking for 1 hour. Shall we take a small break? Yeah, let's take maybe a 5-minute break, and then we'll come back again. We'll talk about linear independence and then linear transformations. So that will be the story for you. Okay. So yeah. Okay, I'll see you in a couple of minutes. Okay. Any more questions?
So Peter, is the P is like a vector, is a fixed vector that we have no, and
B on the right hand side, the B, this one.
Yeah, I know B. I mean the last page you show on the Wolfram mathematical that page, you write x then a equals x equals p. I forgot. You write on the last page. Sorry, I need to check.
This one, right?
X equals p plus vh.
Yeah.
Right, that one.
So,
yeah, it's the p. It's like the p means a fixed word.
Well, P is any solution. Well, let's check. So it's any solution of the inhomogeneous equation. Let's check, right? So the vector P from that slide was this. So I'm not gonna, let me not put back the mathematics. I'm just going to copy it here. So vector P was -1, 2, 0. Let's check that if you plug x instead of x, you plug p, you'll get a solution. So a times p is equal to what? It's 3, 5 minus 4, minus 3 minus 2, 4, 6, 1 minus 8. Now multiply this matrix by vector -1, 2, 0. Which vector are you going to get?
B for 7, -4, -4.
Yep. So that works, right? So that this is equal to B, which means that P is one of the solutions, right? There are infinitely many solutions, and P is one of them.
Oh, and what's the meaning of VH?
Now, good. So VH is a set of solutions of the homogeneous equation of AX equals 0.
So it's like there's like if there's
solutions, that's a solution of AX equals 0, which we know what it is, right? It's here in the on the iPad. It's this, right? It's any it's the span V, right? So it's not any. So X can be any vector which has coordinates. This one, right? For third 0, 1 multiplied by any number.
So that means that in XH, all the elements we know, the variables we know, we cannot know exactly the answer it is, but we can know the relationship between them.
I don't quite understand. So no, so here, so the claim is that every solution of the inhomogeneous equation you can represent it in this way. So it gives you the algorithm of finding the set of solutions for the inhomogeneous equation once you know the set of solutions for homogeneous equation. Okay, so let's say we know the solution of homogeneous equation. So VH is a vector from a set from the set of solutions of AX equals 0, right? It's that vector. It's that any vector that is proportional to vector V that we had above. Okay.
Okay, I got it.
And now claim, in order to find a solution of the inhomogeneous equation, you add P, where P is absolutely any solution of the inhomogeneous equation. So just to illustrate, you could have found a different P, right? So for example, well, I mean, you can try to find a different P, right? So if say you find a different P, then the formula would still be true. It's just the same point X, the same solution will be given by a combination of of different vectors. But regardless, if you talk about the set of all solutions, the statement holds, right? It's that sort of the translation by P of that line or of that span of solutions kind of explains that.
Is here X performed in perform homogeneous equation?
No, here is for non-homogeneous equation. So this X is this X here. So so what's here in the bracket, in the purple bracket, is the description of the set of solutions of the full inhomogeneous equation.
Okay, I got it.
So it might look a bit strange that you can take any solution of a non-homogeneous equation, but it's really not surprising given the fact that you have these two parallel lines, right? So if you pick a different different solution, sort of then you'll just take a different solution from the homogeneous equation, which will get you the same X. Okay, I think I know how to explain good. I think let me show you. Otherwise, it's a bit confusing. Okay, sure. Let's spend a little bit more time on this. So let's check that what I said is true. Okay. How we're gonna do this? Let's just substitute this X into the equation. So checking. So AX is equal to A multiplied by P plus VH. Okay? So it's equal to A multiplied by P plus A times VH. What is A times P equal to? We just calculated it, right?
B.
B, right? That's B. What's A times VH equal to? Remember what VH was. VH is the solution of homogeneous equation, which means that this is equal to what? Iris, what do you think?
I don't know.
So by definition, homogeneous equation is this, right? So this is zero vector.
Okay.
So this works. So our check works. It's equal to B.
Oh, I know. Okay.
Does it make sense now?
Yes.
Yeah. So see, yes, like it may look, and then here you can see that if I replace P by any other solution, say some vector P prime, it will still work, right? Because AP prime will still be equal to B, and A times VH is still equal to 0. Yeah. So like it absolutely has to be any solution of the homogeneous equation, of the inhomogeneous equation. There will be exercises. So if you haven't started doing exercises here, so that's the, what is it? It's section 1.5, I believe, right? Yes, 1.5. So do some exercises from section 1.5, and there are practice problems and solutions of practice problems. If you have questions, we can talk about them on Monday, or you can ask your TA. Do you know who is your TA? Do you have her contact?
Yes, we have.
Yeah. But yeah, so like I think we just haven't gotten to this topic yet. Yeah, so it's okay. But I think but now you should see why this is the case. And in fact, it's a general phenomenon. So like later when you study some other topics in mathematics, like differential equations, for example, there's a similar statement there. So there is a notion of a homogeneous equation when there's a 0 in the right-hand side, and the inhomogeneous equation when there's some function on the right-hand side. And the recipe to find solution is literally the same. First, you find space of solutions of the homogeneous equation, and then you need to add to it any solution of your inhomogeneous equation, and you are done. You will have described the full set. And the theorem is proven the same way we just proved our theorem. Good. Okay, so next story is linear independence. So the definition, so that's a set of vectors v1 through vp inside Rn is linearly independent if the only linear combination of these vectors which is equal to 0 is trivial. So in other words, C1 V1 plus and so on plus C P VP is equal to 0 implies that all C's are equal to 0. So that's linearly independent, and the counter, and then the sort of the opposite is linearly dependent, and then it's called, so this set V1 through VP in Rn is linearly dependent. Well, if in the same setup there is a non-trivial linear combination, right? If for C1 V1 plus and so on plus CP VP equals 0, there exists so some at least one of C of this coefficient is non-zero. At least one of C1 through CP is non-zero. So in other words, there is a non-trivial linear combination which is equal to 0. Or there exists a non-trivial which is equal to 0. Yeah. So I write it down because I mean these terms they used abundantly in the literature. So in the books, you're going to hear them a lot all over the place if you haven't heard already. Right. So examples. Vector say v1 is equal to 0, 1, v2 is 1, 0. Are they linearly independent or are they linearly dependent in R2? What do you think? So if we do C1 V1 plus C2 V2 and put it to 0.
It's gonna be independent.
Yep, that's right, because that means that C1, C2 equals to 0, right? Which sort of tells you on the nose that C1 is 0 and C2 is equal to 0. So these vectors are linearly independent, right? So it's the first example. In fact, we have 2 dimensions that these are nothing but the basis vectors in 2-dimensional Euclidean space, right? So they are, of course, linearly independent. How about these vectors? 1, 1, 1, 0, 1 minus 1. Let's call them V1, same names, V1, V2, V3.
So how this works is like C1 times V1 plus C2 times V2 and plus C3 times V3.
Yeah, so to answer the question, you need to show if there is a non-trivial linear combination which does. So let's do that.
Oh.
So now put it to 0. So is it possible or is it not possible to find non-zero C1, C2, and C3, at least one of them non-zero, such that this is true?
When C1, C2, C3 both equals 0, it's gonna be true.
So no, of course it's always correct. So it's always possible to put them all to 0, but it's not interesting in a sense, right? Like it's always the case. Question is whether we can find. So in previous example, it was not possible for sure. So the 0 C1 equals 0, C2 equals to 0 was the only choice, right? And that's why these vectors were linearly independent. But let's look here. Can we find some combination of these numbers so that the vectors will not be linearly independent? Or
I think V2 can be -2 and add them together.
and
Or is
minus
C1 is
1, right? Yeah,
Yeah.
that's so indeed. So if you do it like this, so that works.
So
So
C1 and C3 is 1.
1 minus 2 and 1, right? Do you agree, Sophie?
Yeah, I agree.
Yeah. So here, this is an example of a non-trivial linear combination of 3 vectors in R2, which is 0, right? 0 vector here. And therefore, these 3 vectors are linearly dependent. And then you can guess that, well, in general, so if you have vectors, V1 through Vp in Rn. So what should be the relation between n and p? Like what is the connection between n and p such that these vectors can be linearly, so when can these vectors one can be linearly independent and one can be linearly dependent?
When is equals to 0, it's gonna be independent, and equals to b will be dependent.
N? So the question is also here, okay, maybe I need to refine the question. So here, see, you had two vectors. In the first example, we had p equals 2, n equals 2, right? And we concluded that these vectors are linearly independent, right? Now here, in the second example, p was equal to 3, n was equal to 2, and we have concluded that they're linearly dependent. Okay, before we go there, how about if we have 4 vectors, say maybe, let's even exaggerate. So we have 10 vectors in 2-dimensional space, v1 through v10. Do you think they'll be linearly dependent or linearly independent?
Dependent?
Sure, yeah, that's right, because there's simply only 2 constraints, right? So the reason why we can talk about this is that actually this condition, we can view as the homogeneous system of equations, right? We can write it as matrix A multiplied by vector of coefficients C equals to 0, right? Simply we can conclude by the size of the matrix, right? So if the matrix is such that it has more columns than rows, right? Then necessarily you will have 3 variables, right? So when you reduce it to echelon form, it will look like this in general. So there must be 3 variables somewhere, right? And because there are 3 variables, you can always so these 3 variables will give you the space of solutions of the equation, which would in other words, if p is bigger than n, right, then we may find the space of solutions of this homogeneous equation, which in this different language will correspond to the fact that all vectors are linearly dependent. So So in other words, the number of equations, right? So here there are 2 equations. Well, if you want to write it, let's maybe write it in. Let's do this one example. I'm gonna write it here. So it will be what, C1 plus C2 plus C3 equals 0, and second equation is C1 minus C3 is equal to 0. So we have 3 unknowns and 2 equations. So most likely there will be a free parameter. So here in this example, there are 10 unknowns and 2 equations. So there will be like 8 dimensional, there might be up to 8-dimensional space of solutions. So here, of course, they will be linearly dependent. Right. However, so in other words, we can say that if P is bigger than n, then we know for sure that vectors will be vectors. Well, I mean, there's some there is some caveats. So like they cannot be arbitrary vectors, right? Like if you say pick a vector which is we need to assume that these vectors are not parallel to each other, right? So let's say assume that they're not parallel. Assume not pairwise parallel. Otherwise, if they're parallel, you can remove one of them from the set. It will not change the outcome. So if P is bigger than n, these vectors are linearly dependent. And then if P is less or equal than n, they'll be independent, linearly independent. Okay. So simply, in terms of this matrix counting matrix equations, you'll have, in the second case, you'll have less constraints, less unknowns than equations. Okay, questions? So just we can reformulate the result that we already know in terms of this language, right? So so if you have a matrix A, which looks like this, and which has column vectors, which we denote as, so A is a matrix with column vectors A1, A2, and so on, AM. Right, so we can say that if the column vectors A1 through AM are linearly independent, then equation AX equals to 0 has only trivial solution. Right? Because, well, this fact is simply just it's not really a theorem, it's just a restatement of the fact that vectors are linearly independent, right? Because this equation is nothing but A1 x1 plus A2 dot x2. There's no error vector here. Plus and so on plus AM xm equals to 0. So the fact that these vectors are linearly independent means that the only linear combination which is equal to 0 is the trivial linear combination, which forces all these numbers to be equal to 0. Okay. Does that make sense?
Yes, yes.
And for example, if you have a matrix like this, 1, 0, 0, 0, 1, 0, 0, 0, 1, acting on the vector A1, x1, x2, x3 equals 0. So clearly these three vectors are linearly independent, the column vectors of the matrix, right? They're independent because, there's one in different position and zeros in the others. So from here it follows that x1 equals x2 equals x3 is equal to 0. So you can see here, in terms of echelon decomposition, every column is a pivot column, right? So there are no free parameters. That's yet another way to say the same thing. Okay. Right, so yeah, okay, good. Right, so I think, yeah, so I encourage you over the weekend to do more, to do exercise, right? So they're due next week. If you feel like you need more time, I think that's okay. I mean, I know that it's a pretty intense week for when it's an intense course. Do you think you have enough time to do the homework, or? So I asked Iris, Sophie, how's your homework going on?
I am okay.
Okay, yeah, sure. Yeah, okay, so yeah. Good. Okay, and then the last story for today will be linear transformations. Then we'll go to the top of the page.
So Peter, I have seen exercise in 1.5, and there's a homework is about how to state whether the A is row equivalent. How to?
Do you have some particular exercise in mind? Which one? What's the number of the exercise?
7 in the textbook.
Yeah. Describe all solutions of Ax equals 0 in parametric vector form, where A is the row equivalent to the given matrix. Oh, it just says that A is that matrix, right? So it's the, yeah.
Okay, I got it, thanks.
They just said it in a fancy way. So like all example, yeah, go ahead.
And what's the, and I have no idea what the 21 means. Like it just gives the matrix, but I don't know how to deal with it.
You read above, it says in exercises 21 and 22, find the parametric equation for the line M through points P and Q. So P and Q are...
So just draw the line? Or...
So you need to write the equation for it.
Okay, thanks.
Yeah. So yeah, I think we talked about it later. So like put a point on the line and then, yeah, so it should describe all points on the blue line. And if you have questions, you can send me an email, anytime. I should go either to myself or to the TA. If it's some simple homework question, you can. I think it will be faster with the TA, probably in a WeChat group, right, or something like that. I used to have a WeChat account, but somehow last time I was in China, there were some regulations like for foreigners, like you need to have your account to be verified by someone. So yeah. Yeah, I have it somewhere, but at the moment it's not operational. Yeah, last time I've been to China was in December last year, before the COVID started. There was a conference in Sanya in the Hainan Island, and it was very nice. It was one of my last trips. Okay, so yeah, let's get back to this talk about the linear transformation. You can see that everything we talk about this week, so in a nutshell, these are the same objects. We just describe them using different words, right? So for example, if you have a matrix A of the size n by m, right? We can just draw it sort of schematically like a rectangle, and basically it's a rectangle which you can fill with numbers, right? So if this is a matrix, so you're allowed to multiply n by m matrices by a column vector with m elements in it, right? So for example, well, have some, a1, 1, a1, 2, a1, 3, a2, 1, a2, 2, A2, 3. Which is the 2 by 3 matrix, right? We can multiply it by the vector x1, x2, x3, and that gives us a two-dimensional vector y1, y2. But you can calculate what this y1 and y2 are, right? It's basically a sum of those elements. Now let's think for a second what this operation represents, right? So you take a matrix. So you start with this vector x, which let's call this is vector x, and this is vector y. So this is vector y. And then so x lives in three-dimensional space. It lives in R3. Y lives in two-dimensional space, R2. And now instead of x, we can put any other triple of numbers. So and then by multiplying it with matrix A on the left, we'll get a two-dimensional vector, which will give us two numbers. So therefore, this A is an operation between three-dimensional Euclidean space and the two-dimensional Euclidean space, right? Which takes vector x with three components and maps it to vector y with two components. So this is what the linear transformation is, right? It's linear because every operation is linear. It's a matrix multiplied by the vector. And transformations means that you had elements in one space, and then after the transformation, you get elements in a different space. So you can write them formally as some blobs. There's one set and another. We'll sort of call it more abstractly. Let's say there's set V and set U, and then there's a linear transformation A, right? That takes element X from here and maps it to element Y from there. That's right. So that's what matrices do. They describe a linear transformation. And I think, yeah, so for, well, we have like a little bit more like 10 minutes left or so. We can look at some examples of linear transformations, and I encourage you to read the book in subchapter 1.8 and 1.9. There are a lot of beautiful examples with pictures. There's no point for me to reproduce those pictures in a notepad or on a computer. So let's just look at some examples. Yeah, I think we can do examples, and I will talk a little bit more about theory next class on Monday. So first, there's the simplest transformation, yeah, and then I think for the rest of the class, let's assume that n is equal to m. So the matrix is quadratic. So we have n by n quadratic matrix, which means that the transformation, so it's a map from Rn to Rn, and both x and y are n-dimensional vectors, right? So the first example of transformation is the identity transformation. Right, and it's given by the matrix. We can call it 1 or I. So 1 is like a matrix. It's a big one, which is, and again, so for simplicity of exposition in here, let's say that it's a two-dimensional space. So n is equal to m is equal to 2. So x and y are both two-dimensional vectors. So let's take matrix 1, 0, 0, 1. So clearly, it's called identity because for every vector x, so for every x, 1 times x is equal to x. Right? Just the way you multiply matrices, right? You multiply 1, 0, 0, 1, x1, x2, it's equal to x1, x2. Then for this example, now, well, let's say do, let's say we stay in 2 dimensions. The next example is the shear transformation. It's given by the matrix, so let's call it S, which looks like 1, 1, alpha, and here is 0. So let's see what it does, right? So S times X is 1 alpha 0 1, acting on x1 x2, gives x1 plus alpha x2 x2. So we can draw the picture, we can draw what's going on. Right, so if before, say we had a rectangle, like this in xy plane. So there's or like a square, right? So this is point was 1 1. This point was 0 1. 1 0 and 0 0. So let's see what happens under this transformation. S with the corners of the square. So here's the formula, right? So we need to substitute instead of x1 and x2, we need to plug in values of those vertices, right? So when so 0 0 becomes 0 0. Now 1 0 still stays, right? 1 0 still stays at 1 0, but the rest will shift a little bit. So under this transformation, 0 1 will become what? What will be the, where will the 0 1 go?
Two, one.
Well, I mean, it's alpha, right? So it's not 2, it's alpha. It's just it's a coefficient. But just for the sake of argument, let's call it so alpha. Let's put the value of alpha to be equal to maybe 0.5. So then it will be as you said, it's 1/2 and 1. So it will go like here. And then vertex 1 1 will go to where? So plug it in here.
Sorry, why is the 0.5?
I just assign it. So like it's alpha is any number, and I just put it to be 0.5. So it will be easier to draw.
Okay.
Yeah, I mean, in fact, so this shear transformation, it depends on this parameter alpha. Like it's a family of transformations, right? It's well, after we draw the image, the draw what happens to the square, you'll see why it's called shear. So where will point 1, 1 go?
So 1.5.
Mm-hmm. Yeah,
and
that's right. 1.5
1.
and 1, yeah. So it will go here, and then you can imagine that the other points will do that. We do like this. So that's why it's called that's why it's called shear, right? Like you basically take it kind of thing, and then you would you know, move it like that. Like you keep the base, and then you would move it sort of parallel with some shift. Yeah, that's another example. Okay, so we're running out of time, but I think last time before I go, I'm going to mention. So there's some terminology here. So if you have a transformation like this, then this set V is called domain. I mean, it's the same as with functions. So it's domain of A. U is called the codomain, right? And then if X goes to Y, we call Y the image of X. Right, and then if if X goes to Y, and then we can say that X is the pre-image of Y. So we have a couple of minutes. Okay, let's not rush it. Good. So I think so like we still need to. I mean, I think we can do. So you can read through the rest of section 1.7. There are some examples for this linear transformations. And if you have any problems, let me know. If needed, we can postpone the homework assignment. Like if you want, I can move the problems from 1.7 to the next homework. Probably that will be more fair. So because I do want to talk about those things. Okay, does it sound good? But if you feel like you want to do them yourself, please go ahead. If not, then I can just reassign it to the next homework. We can decide on Monday.
Okay.
Good, sounds good. Great. Have a great weekend. Have a productive weekend, and see you next week then.
See you next week.
Okay, bye.